Welcome to the Earth's heartbeat. Ocean currents act as a massive global HVAC system, moving incredible amounts of heat from the sun-drenched equator towards the freezing poles. By constantly circulating this thermal energy, these currents prevent our tropical regions from literally overheating, while keeping our higher latitudes habitable for billions of people. They are truly the engine of our climate system, regulating the temperature balance that allows life on Earth to thrive. Without this global conveyor belt, the world would be an extreme and uninhabitable place. Let's dive deeper into how this spectacular process works. Prepare to be amazed by the Earth's most incredible underwater engine, the Thermohaline Circulation. It's the ultimate global conveyor belt, moving water across every single ocean basin. The name thermohaline comes from two words, thermo meaning temperature and haline meaning salinity. Together, they create a density-driven loop that is unstoppable. As water flows toward the frigid poles, it loses heat and becomes much saltier as ice forms. This makes the water incredibly dense, causing it to plunge deep into the ocean depths, creating a vacuum that pulls warm surface waters from the tropics to replace it. It's a massive, planetary-scale dance that regulates our climate, keeping our world habitable. This isn't just water moving, it's the heartbeat of our biosphere. Welcome to the high-speed lane of our oceans. While deep currents move slowly based on density, surface currents are governed by global winds and the incredible Coriolis Effect. The Earth's rotation exerts the Coriolis force, which deflects moving air masses. This interaction creates massive circular patterns known as gyres, the primary drivers of surface flow. Take the Gulf Stream. It is effectively an ocean-bound river, pushing massive amounts of warm tropical water at high speeds across the Atlantic basin. It is a vital transport highway for thermal energy. These surface currents are the dynamic engine room of our climate, distributing heat with incredible speed across the globe. Did you know the ocean acts as the Earth's ultimate heat sponge? It absorbs a staggering 90% of all excess heat trapped by greenhouse gas emissions. Ocean currents serve as a massive conveyor belt for this energy. They capture the heat at the surface and transport it deep into the ocean's interior. By storing this energy far beneath the waves, the ocean effectively buffers our atmosphere, preventing much more rapid global temperature increases. It is a vital service that keeps our planet habitable. We are witnessing a defining moment in climate history. Recent 2026 data confirms the Atlantic Meridional overturning circulation is at its weakest point in over a millennium. Our latest observations show a staggering 15% slowdown since the mid-20th century. This isn't just a number, it's a vital pulse of our planet's thermal regulation system. This weakening of the AMOC is officially the most critical variable in our current climate trajectory. It represents a potential tipping point that scientists around the globe are monitoring with absolute urgency. The stability of the global conveyor belt depends on one simple physical truth: density. In the North Atlantic, cold, salty water is heavy enough to sink, acting as the engine that pulls the entire system forward. But we have a major problem. As Arctic ice melts at an accelerating rate, it dumps massive volumes of fresh water into these critical sinking zones. This is not just water, it is a physical barrier. Because fresh water is significantly less dense than salty ocean water, it stays on the surface, creating a buoyant layer. This layer acts like a cork in a bottle, effectively plugging the pump. When this pump fails, the global conveyor belt begins to stall. The heat transport slows, the surface waters warm, and the entire climate system loses its primary thermostat. This freshwater influx is the most immediate threat to our oceanic stability. The Pacific Ocean functions as a massive climate engine. Under normal conditions, strong trade winds push warm surface waters toward the western Pacific, creating a vast, warm pool. But during an El Niño event, these trade winds weaken. This causes that giant reservoir of warm water to slosh eastward across the basin. This single shift in the Pacific triggers a global cascade of extreme weather. We see severe droughts in Australia and catastrophic flooding across the Americas in just one season. It is a perfect example of how interconnected our climate systems are and how rapidly these dynamics can alter life on land. We are seeing a critical shift in our planet's climate regulation. Data from the global Argo float network reveals that even the deep ocean is warming at an unprecedented rate. These robotic profilers have captured a chilling reality. The conveyor belt, our Earth's natural pump, is failing to move thermal energy efficiently. Instead of distributing this excess heat, it's sinking directly into the deep layers. This confirms that our ocean's capacity to act as a heat sponge is reaching its physical limit. The deep ocean, once a cold and stable reservoir, is now rapidly absorbing excess energy from the surface. This is an urgent climate alert. When the deep ocean warms, the buffer we rely on to moderate global temperatures begins to collapse, accelerating feedback loops that threaten our biosphere. The Arctic is warming at a pace far beyond the rest of the planet, a process known as polar amplification. It starts with the albedo effect. Bright sea ice acts like a mirror, reflecting most solar energy back into space. But as it melts, it exposes dark ocean water, which drinks up that solar heat instead. This runaway heating has a massive consequence: a flood of fresh water. As Arctic glaciers and ice sheets melt, they dump vast quantities of low-density freshwater into the North Atlantic. This freshwater creates a low-density lid on the ocean surface. Because it's too light to sink, it effectively jams the global conveyor belt, preventing the heavy salty water from diving into the deep ocean. This is how local Arctic melting triggers a global climate emergency. The ocean is our planet's ultimate carbon vault. It absorbs massive amounts of atmospheric carbon dioxide, keeping our global temperatures in check. However, a critical feedback loop is forming. As ocean currents slow down due to warming, the physical mechanism that pulls surface water and its trapped carbon down into the deep ocean falters. When this conveyor belt stalls, the ocean can no longer pull carbon dioxide from the air. CO2 starts to accumulate rapidly in the atmosphere. This creates a dangerous positive feedback loop. The less the ocean absorbs, the more heat-trapping gas remains in our atmosphere, which only accelerates the global warming that caused the slowdown in the first place. We are entering a critical frontier in climate science, the tipping point risk for the Atlantic Meridional Overturning Circulation. Scientists now view a potential collapse not just as a theory, but as a high-impact risk. Imagine the ocean circulation as a complex machine. If we push it too far, we hit a threshold where the system cannot simply restart. This is the definition of an irreversible climate shift. By 2026, research focuses heavily on this danger zone. While a total collapse is not expected by 2050, the possibility of crossing this boundary is a massive focus for global climate researchers. The risk is low probability, but the impact is catastrophic. If the conveyor belt stops, the redistribution of thermal energy across the globe would be fundamentally altered, changing weather patterns for centuries. Studying these tipping points allows us to define the safety boundaries for our planet. Every fraction of a degree in global warming matters in keeping the system within its stable state. A major slowdown in ocean currents is not just a global temperature issue, it's a catalyst for regional chaos. Let's look at three critical impacts. First, the Atlantic Meridional Overturning Circulation is essential for keeping Europe mild. A collapse means severe cooling for the continent. Second, the U.S. East Coast faces accelerated sea level rise as the currents that currently pull water away from the coast weaken. Finally, massive shifts in heat transport disrupt the intertropical convergence zone, causing total failure of essential monsoons in Africa and South Asia. These are not just theoretical models. They represent a fundamental reorganization of the world's climate, threatening agriculture and coastal security everywhere. Think of the ocean as the Earth's massive thermal battery. Due to its incredible heat capacity, it doesn't just warm up, it stores that energy for an extremely long time. This is called thermal inertia. This inertia means the ocean has a long memory. Even if we completely ceased carbon emissions tomorrow, the heat already absorbed would keep the climate system out of balance. The ocean is locked into its current state by the heat it holds. The currents that regulate our climate are effectively carrying the legacy of our past emissions, meaning our disruptions will persist for centuries to come. Ocean currents act as the engines of global nutrition. They pull nutrient-rich waters from the depths to the surface, creating the vital foundation for all marine life through phytoplankton growth. However, as these currents decelerate, the nutrient pump fails. This triggers a catastrophic cascade, leading to the collapse of marine ecosystems that provide essential protein to billions. Beyond the oceans, current shifts disrupt the monsoon patterns critical for agriculture. With erratic rainfall, food staples for South Asia and Africa are increasingly threatened, pushing the world toward a systemic food security crisis. We are at a crucial junction. To preserve the life-giving ocean currents that regulate our planet, the IPCC is adamant. We must stabilize global temperature rise between 1.5 and 2 degrees Celsius. Every single fraction of a degree matters immensely. When temperatures climb, polar ice melt accelerates, injecting massive amounts of freshwater into the North Atlantic. This freshwater acts like a barrier, preventing surface water from cooling, becoming dense, and sinking. This shuts down the global conveyor belt pump. If we exceed the 1.5-degree threshold, we risk hitting a catastrophic tipping point where current weakening becomes irreversible. This is why our climate goals are not just numbers. They are the safeguards for planetary circulation. We are no longer guessing about our oceans. With the revolutionary global Argo float network, we have deployed thousands of robotic sentinels across the planet. These autonomous floats descend into the depths to capture high-precision data on temperature, salinity, and current velocity. Once they complete their profiling cycle, they ascend to the surface and transmit their findings directly to satellites. This real-time global observation system provides the high-confidence trends we absolutely need to plan for the future of our changing climate. We must remember, the ocean and the atmosphere are not separate entities. They are one tightly coupled system. You cannot shift the temperature of one without triggering a massive, immediate response in the other. Currents act as the vital bridge, the heartbeat that maintains balance across the entire planet. They move heat, carbon, and moisture between these two domains, ensuring our climate remains habitable. Think of this as an engine. When ocean currents circulate warm water to the poles, the atmosphere receives that thermal energy, driving global weather patterns. This isn't just movement, it is the fundamental engine of our global climate. We are synthesizing a massive amount of data. By combining satellite observations, deep-sea robotic Argo floats, and advanced climate models, we have achieved a crystal-clear picture of our changing oceans. This data convergence reveals a sobering reality. The ocean's incredible service of regulating our global climate is not infinite. It is being pushed to its physical limit by rapid, human-induced warming. By synthesizing these independent data streams, we no longer guess. We know that the tipping point is closer than ever, demanding immediate action to protect our climate heartbeat. Understanding the ocean's intricate circulation is the foundational step toward global intervention. By mapping these massive thermal flows, scientists are gaining unprecedented visibility into our climate's engine. Advanced robotic sensors and high-resolution satellites allow researchers to process complex data sets, transforming raw ocean observations into actionable insights regarding current stability. Armed with this knowledge, nations are developing localized adaptation strategies, helping vulnerable regions strengthen their defenses against shifting current patterns and climate volatility.